Okay, so let's take a look at the solution, possibly two different ways. So let me save this because I'm going to refer to it later again. Oh, no. Okay. First way of doing the problem. Once again, the question was, find the fluid force across this triangular plate, assuming that the water level is 3 feet above the tip of the triangular plate. That was the question. Find the fluid force. Find the fluid force across the triangular plate. Okay, first thing is we always select a coordinate system. Let's see, I'm going to select as my first solution a system where the 0, 0 is at the corner of your triangle. Okay. I will pick a representative rectangle from the region. The thickness is delta y, right? Let's first find the fluid force across this thin rectangle, right? So fluid force equals WHA. We're finding it for the rectangle, so I'm just going to say delta fluid force equals. Okay, W we always assume is the same. Okay, what did you use for the depth? Which is this distance. How much that rectangle is underwater. That's causing the force, the pressure, right? So what is that distance? What is the level of this in terms of the given coordinate system? This is the point y equals what? Y equals 12, right? So that distance given by the black arrow, the depth would be what then? 12 minus y. Okay, how about the area? This is the tricky part, the area of that thin rectangle. The thickness is delta y, right? Do I need a 2x here? I almost made the same mistake earlier. I look at this because we've been using 2x almost automatic, but here it's just x, right? We don't need a 2x here. The distance, the length of your rectangle is just x. So this distance is just going to be x. The length and the width is delta y. So the only problem that we have to overcome here is writing x in terms of y. That's the tricky part about this question. Using just your regular similar triangles is not going to work. Here's why. Okay, let me recopy that triangle over here. We have a situation like this. This is x. This bottom is 6. Now tell me what distance here represents y on this triangle. Y is distance to the x-axis, right? So which distance here is y? From here to the rectangle, right? So that's the bottom part is going to be your y, this one right here. Okay. The entire distance is 9. Okay. Then what can you tell me about this distance here? If the longer distance is 9, the shorter one is y, that's the difference of the two, right? Which is what? 9 minus y. Okay, now, which two triangles are similar here? The big one is similar with the one on the top, right? This one. The one on the top. So we have to be very careful when we're setting our similar triangle ratios. Here's how we can do it. On the big triangle, the ratio of 9 to 6 is equal to, on the small triangle that's on the tip of this figure, what number should I put there? 9 was the height, 6 was the base. Now what should I be putting? What is the height of that small triangle on the top there? 9 minus y, right? And what is the base of that small triangle? It's x. and I need to solve for x in this equation. Again, the way this triangle was placed in our coordinate system, we had to be very careful with similar triangles. We had to notice which two triangles are similar and use their side lengths in our ratios. So if I solve for x from here, I get 9x is equal to 6 times 9 minus y, and then divide both sides by 9. In simplified form, I get 2/3 times quantity 9 minus y. So this is what we should place in for x here. And the 2/3 can be factored outside. Then we can finish the problem from there. It's not going to be that hard. So let's set it up. The total fluid force equals 62.4 times the integral of 12 minus y times x, and x, based on what we just determined, is 2/3 times 9 minus y. And the only thing I need to know from you guys is the limits of integration. These rectangles expand from where to where? Based on the picture that we have, 0 to 9. The rectangles are existing from y equals 0 to y equals 9. Now, I want to show you another way. Say you didn't think about doing this fancy or a little bit unusual similar triangles method. There was another way. You will get the equation of this line, the one that we have here, the red line up there on our first picture. What is the equation of this line? We know 2 points there on the line, right? So we could get the slope, and from there we could get the equation of the line. So, for example, this is a point on that line. What is that point? 6, 0, right? And this is another point on that line. What are the coordinates of that point? 0, 9. So you could now get, okay, what is the slope? What is the slope of this line? So if you're going to do it that way, you need to get the slope. So 9 minus 0 is 9, divided by 0 minus 6 is negative 6, which is negative 3/2. And then I could pick any one of those 2 points. I'm going to pick the one with 6, 0. Actually, let me pick the other one because I'm going to need to solve for x. Pick the one with 0, 9. Y minus 9 is equal to the slope times x minus 0. And solve for x from there. Is this the same thing as that? Let's think about it for a minute. Are these two the same things? Here we're saying x is negative 2/3 times y, not minus 9. Here we're saying x is 2/3 times 9 minus y. Same exact thing, right? Negative, because they switched the 9 minus y to y minus 9. Either way you do it, just carry it all the way through the same way consistently. And again, either approach will give you the correct x. Now, I know you can finish this integral because you would put the 2/3 outside, and you would FOIL it and plug in the numbers. I'm going to give you the answer there because I want to take the time to show you one more way to set this up with a different coordinate system. And that actually turns out to be a little bit easier to solve. Okay, so the answer was, if you finish the entire problem, you should get 15,163. I'll just put that at the moment. 15,163 pounds. If you didn't get it, do it later. Double check this, please. Okay. Anybody who got that far and got all that answer all the way to the end? Yes, question? Yeah, we could not do that because going back to our similar triangle ratios over here, look at which triangles are similar. Which ones are similar? The one on the top, which is this one, right, is similar to this one, the big one, right? So when you are setting up the ratios of your similar triangles, you got to use the size of your similar triangles, because if you use y is not a part of a similar triangle, right? If you look at the size, because on the big one, the height is 9, the base is 6, correct? On the small one, the height is 9 minus y, and the base is x. Okay? See, in the past, we had triangles like this. Let me go back down a little bit to get some space. In the past, we had triangles like this. For triangles like this, yeah, this is y, this is x. You can do that, okay? But this triangle was placed differently. You see the way it was placed? You don't have a y and an x. You have the two similar triangles. The smaller one has a height of 9 minus y and a width of x. The big one has a height of 9 and a base of 6. Because still x is the distance to the y-axis. That hasn't changed. If you look at the picture, x is still x. That didn't change. Yes, Courtney? If the water level was at 9, we still couldn't use it because of the shape this triangle was given to us. Still, it would have to be the same similar triangle ratios as we used here. Okay? Now, there is one more way to set it up. Again, think about this. And if you have questions, also please do see me after class. Okay, another way to set this problem up would have been like this. I'm going to take the same picture, but now impose the coordinate system a little bit differently. And maybe you'll like this a little bit better. And if you didn't like the way we did the similar triangles, then think about getting the equation of the line. That was more foolproof method, you know. Get the equation of the line. You have 2 points. Everybody knows how to get the equation of the line, and then solve for x. You could have done it that way. Okay. So here's how I place it. Once again, I need to pick my representative rectangle with thickness delta y. And first, I need to concentrate. What is the fluid force on this rectangle? W is always 62.4. Okay, H. In this example, how will you represent this point right here? This is my 0, 0 point. So what is this point right here? The depth of water, how will I represent it with this coordinate system? Y equals to what? Y equals to 3, right? So this level is the point 3. This is the line y equals to 3 right now because of the where we place the coordinate system. Okay, I need to know right now H. H is the depth in the water. So what is this depth right now from here to here? Three minus y. Let's check that. Let's say that your rectangle was at a point y equals to -1. Would 3 minus y give you the correct depth? 3 minus -1, that would give you 4, right? That is the correct depth, right? Okay. How about the length of your triangle? Okay, the length of the triangle once again is x, right? And the width is delta y. Once again, I need to get rid of the x in terms of y, but it's a little bit easier this time. Either write the equation of that line goes through 0, 0, it's a lot easier, or look at it this way. This distance is your x, and how about this distance? -y, very good. Now, which two triangles are similar? Once again, the one on the tip with the big one. How would you set your similar triangle ratios now? On the big one, the ratio of 9 to 6 equals what on the small one? Negative y to x. I need to know what x is, because we're talking about, and we're below the x-axis. That is why. That distance is kind of like 0 minus y in a sense. So we're getting x is equal to negative 2/3 times y. We can put that information in here. Bring it back up. And again, instead of x, I'm going to put negative 2/3 y. And in this case, I should integrate from where to find total fluid force? Look at your rectangles now. From where to where are your rectangles extending? From anywhere from, what is this point right here? Negative 9 to where? To 0. 3 minus y times y I leave inside. Negative 2/3 I pull outside. And don't worry about that negative. Eventually it will disappear. This one is so much easier to integrate than the other one was. The other one you have to FOIL. Here there's nothing to FOIL. Just integrate. Integral of 3y is this. Integral of y squared is this. And go from negative 9 to 0. When you plug in 0, you get nothing. And then let's just plug in what we get when we're plugging negative 9. Yes. Yes. Because this triangle was placed below the x-axis. It was in the negative y region. That is why. On the first triangle that we did, the first method, let's go back up there. Because there, my triangle was above the x-axis. The distances were positive there. X's were positive, and the y's were positive there. Okay, do you realize what y represents in this picture, the first one? Right, y is here. That is y, right? So if I do y over x, I'm forming a ratio of something that is not even a triangle. That bottom quantity there, the bottom area, that is not even a triangle. Right, I need to form the ratio of the size of a triangle. So that's why I need 9 minus y to x on the first one. Okay, I'm going to come back and answer any other questions you may have in just a moment, but finishing this one up, if we plug in negative 9 for y, let's see what we get there. Okay. I'm getting 364.5. But again, the two negatives will turn out to be a positive quantity. I'll just multiply those now. And we're getting the same answer as I gave you earlier, 15,163.2 pounds. Okay, I'll go back and answer any questions you may have, but the bottom line is you have more than one way to do these questions. And if you happen to have the extra time in your hands, do it two ways, and then make sure you're getting the same answer eventually. It's really good brain exercise in a sense, and also a way to check your own answers. If you can do it both ways and get the same answer, you know for a fact you got the correct answer. But in general, I would recommend you do it the way that is easiest for you, whichever method that may be. All right. All right, let us take a look at this next example where we have a trough with a trapezoidal cross section, and let's assume it's full of water, and the question is to find the fluid force exerted upon the trapezoidal and the cross section that we see here. So this is just like a a vertical plate submerged in water type of example. The question is, where should we locate the coordinate system? And by the way, I should tell you the height of the trapezoid, that should be 5 feet. Okay, so where to place the coordinate system? Let's think about that for a moment. Okay, now I do see some obvious symmetry here, so it's always a good idea to place the y-axis along the axis of symmetry if you see such a thing. So in this case, I will select my y-axis to go through just the center of this figure. First, I'm going to clean it up a little bit. Okay, so I'm going to place my center. I don't even need any of this. Okay. Again, I chose to put the y-axis right through the center of the figure to take advantage of the symmetries involved. That way the length of the rectangle will be 2x. And I see no advantage in this case of placing the trapezoid below the x-axis as opposed to above the x-axis. So for this example, we might as well go with the easier approach since there's no advantage of putting it below the x-axis. So as always, begin by selecting a representative rectangle. And we're going to first write the fluid force on the rectangle. The formula is WHA for constant depth. Okay, I better put some numbers on my coordinate system. Okay, so the bottom was 6 feet long, everything in feet. So half of that would be 3, so this point is 3. The top was 8 feet long, so half of that is 8, so this point here would be 4. The height was 5, so this point would be 5. Okay. W is the weight of water, and that should be 62.4. Okay, the depth of this rectangle will be this distance, and that is 5 minus y. The area, that is the length times the width of our rectangle. Clearly the width is delta y, and the length is going to be 2x. All right. Same problem as we've been having all along. You have a dy selected as your thickness, the limits of integration, and the variables of the integral must be in terms of the y variable, but yet we have a 2x. So we need to get rid of that x, and there's no simple triangles that we can use here, because what you really have is not a triangle, but trapezoids. And it gets more complicated. So one suggestion I have for you here is the easiest way to do this would be to actually write down the equation of this line. If we could write the equation of this line, let's see, that would be this line right here. If we could write the equation of this line, then we know that that line will relate x in terms of y and y in terms of x, and we can get rid of this x then. Okay, to write the equation of that line, first notice 2 points that are clearly on this line. Okay, the bottom point is the point 3 comma 0, and the top point is the point 4 comma 5. So first I need the slope. Slope is 5 minus 0 divided by 4 minus 3. The slope is 5. To get the equation, I'm going to use the point 3 comma 0. So I go y minus the y coordinate equals slope times x minus the x coordinate. So I'm getting 5x minus 15 as y. But remember, I need to know x in terms of y. So let's do that. Y plus 15 equals 5x. So x is equal to y plus 15 all over 5. Now we can put that information up here. 62.4 times 5 minus y times 2x, which will be 2 times quantity y plus 15 over 5. I might as well put that as 2/5. The denominator doesn't really matter. And now we need to integrate this to find total fluid force. So the total fluid force equals 2 times 62.4. That's 124.8 divided by 5. Inside the integral, I'm going to need 5 minus y times y plus 15 dy. And let's think for a moment about the limits of integration. These rectangles along the y-axis, they're going to be going from where to where? You were right if you said from 0 to 5. And once again, this doesn't become a difficult integral, it's just tedious. We just have to FOIL it out first. So let's see, I have 5 times y, then 5 times 15, then negative y squared, and negative 15y. Same limits of integration, 0 to 5. Let's clean it up a little bit, and then we will integrate. So the negative 15y plus 5y, that's negative 10y. I have, first of all, negative y squared minus 10y plus 75. Integrated with respect to y from 0 to plus 5. Okay, integrating each piece, we get the following. And let's go ahead and take a moment to evaluate this. Just plug in 5 for y, minus when we plug in 0, we'll get nothing. So we just have to worry about what happens when we plug in a 5. So let's take a moment to do this. Okay, so if you got 5,200 pounds, you got it right. So the total fluid force across the vertical end of this trough that is filled with water turns out to be 5,200 pounds. Now, I want to show you one more way that you could have done this question. It's a little bit tricky, so it's completely optional. If you don't want to get confused, you can stop the video right here. But I like these different viewpoints. I think it might help you on another question to do the problem slightly easier. So I'm going to copy that shape down one more time. And this method, you don't have to use the equation of the line. Okay, let's plug it right here. Okay. Okay, I'm going to try to use similar triangle ratios in this case. But I need to clean up my figure a little bit better than that before getting started. So let me do that. Okay. So once again, this side was at 3. This was 4. Okay, I'm going to try to use similar triangles on this triangle at the very end here. And remember, we had a representative rectangle selected from the region. Now, I know that distance from here to the end is x. And I also know distance from here to here is 3. So I could actually represent that this little distance here, let me do another triangle so you can see better. So this distance over here, so once again, the entire thing was x, this was x, this was 3, so that's the difference. That's going to be x minus 3. Okay. This distance is y because it's distance to the x-axis. So this distance is y. The bigger distance on the outer triangle, the height is 5. And because this triangle was formed between the point 3 and 4, the base of the outer triangle is going to be 1. So now if I form a similar triangle ratios, so this is the big one on the outside that is similar to this one on the inside. So on the outside, the ratio of 1 to 5, which is the ratio of base to height, on the inside that will be equivalent to the ratio of x minus 3 to y. Now I need x in terms of y, so I'm going to solve here. So I'm going to have y over 5 is equal to x minus 3. Therefore, x is equal to y over 5 plus 3. Now let's compare this with the other answer we got with the equation of the line. What do we have for x way up there in the beginning? We had x is equal to y plus 15 over 5. But if you simplify that, you could certainly write that as y over 5 plus 15 over 5. In other words, y over 5 plus 3. Again, looking down, y over 5 plus 3 is exactly what we got with this approach as well. Again, it was a little bit trickier. In my opinion, writing the equation of the line is more foolproof method. So whichever one is the one you prefer, you should use that one.